SwayamPrabha. Digital India. Educated India.
In this lecture, we are going to look at spatial kinematics of rigid bodies. To give you an overview of what we are going to discuss, we are going to look at kinematics in 3 dimensions. We are going to look at a prototype problem, which will be essentially will set the tone for kinematics of rotation about a fixed point. Spatial motions can be considered to be essentially 2 types, where at least there is a fixed axis, which is called a fixed axis rotation, or it is also known as parallel plane motion. It might seem that this is very similar to planar kinetics what we have studied, but it is not, as we are going to discuss very soon. The other is fixed point rotation, rotation of an axisymmetric body about a fixed point. The next would be completely free motion of a rigid body, that we are going to discuss a little later. We are going to start with this prototype problem of rotation about a fixed point, rotation of a symmetric body about a fixed point. The parallel plane motion we will discuss a little later. Here I have shown in the figure an axisymmetric body rotating with this point at the origin of the x naught, y naught, z naught frame. That point is fixed. The body is spinning, the spinning angular velocity is omega s. There is something called a precessional motion, which is indicated by omega p about the vertical axis, and there is a nutational motion, which is about that x axis. Let us first look at the various coordinate systems. X naught, y naught, z naught is the inertial or the non-rotating coordinate system. Its origin is at the point of fixation of the body. The z axis, now we are going to study the or discuss the x y z frame, how to set it up. The z axis is along the axis of spin, it is the spin axis of the body, and the spin vector is omega s. The x axis, this is the x axis, it is determined by the cross product of the z naught axis and the z axis. This is the z naught axis and this is the z axis. The cross product of these two is the x axis. Thus, x axis is perpendicular to both z naught and z, and this x axis will always be in the plane x naught, y naught, because it is perpendicular to z axis, and therefore, the any direction perpendicular to the z axis must be in the x naught, y naught plane, perpendicular to the z naught axis. Any vector that is perpendicular to the z naught axis must be in the x naught, y naught plane. So, here we have the x axis, and y axis completes the right handed system x, y, z. Now, x, y, z is a rotating frame. Why is it a rotating frame? Because that z axis, the z axis is rotating about the z naught axis. This is called precessional motion. The angular velocity of the frame x, y, z is given by capital omega f, that is equal to omega p, which is the precessional motion, plus the nutational motion. You can now see that the precessional motion omega p turns the x, y, z axis. the precessional motion, it rotates the xyz axis. Therefore, this angle is, if I call this angle as psi, then psi dot is the magnitude of omega p vector. This is one. The other is the nutational angular velocity. Here is the nutational angular velocity about the x axis. If the body tilts, if this angle theta changes, then you have omega n. Therefore, theta dot, rate of change of theta, will give you the magnitude of the nutational angular velocity of the frame. Therefore, the frame angular velocity is composed of two parts, omega precession plus omega nutation. That gives us the angular velocity of the frame. Therefore, the total angular velocity of the body is the angular velocity of the frame plus the angular velocity of the body in the frame or with respect to the frame. To an observer in the frame, to an observer who is fixed to the xyz frame, that observer will see the body spin about the z axis of the frame. The absolute angular velocity of the body, therefore, is the angular velocity of the frame. This is the angular velocity of the frame plus the angular velocity of the spin. Here I have written out these two angular velocities. One is of the frame, which is omega p plus omega n vectors, and the total angular velocity of the body, which is omega p plus omega n plus omega spin. Now, angular acceleration. Whenever I have to derivate now, because we are in a rotating frame, x y z is a rotating frame, if I have to find out angular velocity, I have to derivate with respect to time the angular velocity vector. Because we are in a rotating frame, therefore, d dt operator becomes del del t, which is the local derivative as seen by the observer fixed to the frame, plus omega frame cross. This we have discussed in kinematics. Therefore, angular acceleration of the body will be given by d omega dt. It is the rate of change of the angular velocity. Now, there are three terms because of the local derivative, and because of the frame rotation you have omega frame cross the vector. So, this is the thing, this is for the local derivative del del t plus omega frame cross the total angular velocity vector. Now, the because of the frame rotation, what I have here is omega f is omega p plus omega n, and here in the total angular velocity vector as well you have this omega p plus omega n. Therefore, the cross product of these two will be 0. Therefore, only thing that remains is the cross product of omega p plus omega n with omega s. Therefore, omega f cross omega s, that is the contribution from the frame rotation term. The first three terms is the local angular acceleration as seen by the observer fixed to the frame, and the second term is the because of the frame rotation. Therefore, in a slightly simplified form you have this expression of angular acceleration of the body. The first three terms because of the local derivative, local rate of change, and the second term in blue, that term is because of the frame rotation. Now, that was angular velocity of angular acceleration of the body. Next we look at the angular acceleration of the frame. Now, for that also I have to take the time derivative of omega f, capital omega f, I would take time derivative, therefore, I must have a local derivative, these two terms, plus omega f cross, and because we are derivating omega f itself, so omega f cross omega f must be 0. Therefore, this is the acceleration of the frame, angular acceleration of the frame. Consider now a point A as shown in red on the disk. I want to express the velocity, the absolute velocity of this point. Velocity of point A in terms of velocity of a convenient point which can be O. O is the origin of the frame. Therefore, velocity, absolute velocity of point A is velocity of O, which is 0 of course, plus V rel, the relative velocity as seen by an observer in the frame, plus omega frame cross OA, the OA vector. You will find that V rel is because of the spin of the body. The observer on the who is fixed to the frame will see the body spin, and only because of that the V rel is produced. Therefore, V rel will be omega spin cross OA, and omega frame cross OA will be omega p plus omega n, which is omega frame cross OA. Therefore, V A is equal to the sum of omega s, omega p, omega n cross OA. I have pulled out this OA out. Next, we look at the acceleration of point A. Once again, I express it in terms of acceleration of O, and then there is A rel term which will be generated because of the spin of the body, plus alpha of the frame cross OA plus omega frame cross OA plus 2 omega frame cross V rel. We know all these terms, and we can plug in various values. Here I have made a simplification, if you like, but this is the most general expression. You can plug in various vectors and find out, but suppose omega spin is constant, it is constant in various many cases. If omega spin is constant, then A rel is given by omega s cross omega s cross OA. This is the centripetal term. Had there been a change in the spin angular velocity, then you will also have the tangential acceleration of point A coming in the A rel expression. But since omega is assumed to be constant, you have only the centripetal term in the local as seen by the local observer. Let us now move to some problems. This is a problem from the book of Merriam and Craig Dynamics. This says a spool A rotates about its axis with an angular velocity of omega A is equal to 20 radian per second. Simultaneously, the assembly rotates about the vertical axis with an angular velocity omega 1 equal to 10 radian per second. Determine the magnitude omega of the total angular velocity and alpha the angular acceleration of the spool. Now, this system falls under is an example of our prototype system, and this spool can be considered to be rotating about that point O. First, we fix a coordinate system, a suitable coordinate system. The coordinate system that we have discussed for our prototype problem, we will extend that here. As you can see, I have made a little bit of change in the way I have marked the x y z axis, but we have this z naught about which you have omega 1 with which the whole assembly is rotating, and z is the spin axis. what I have done is I have taken y this time, y axis, which is common normal to z naught and z, and x is the corresponding right handed coordinate system. Now, omega a, this is angular velocity of the spool, angular velocity of spin. So, this is the spin angular velocity of the spool about its own axis, omega a, written in this coordinate system x y z. I am using this coordinate system x y z. I will express all vectors in this x y z frame, and omega a, which is the spin angular velocity of the body, is 20 k cap radian per second. Omega 1 now also has to be expressed in this x y z frame. It makes an angle 60 degree with the z axis. Therefore, this is the magnitude omega 1, this is the magnitude of omega 1, and this is the direction expressed in the x y z frame. And this is the angular velocity of the frame. Omega 1 vector is also the angular velocity of the frame. Therefore, omega spool, the net angular velocity of the spool is omega 1, which is the frame angular velocity, plus the spin angular velocity with respect to the frame, which is omega a, and I calculate these terms and plug in to find out the net angular velocity of the spool, and this is what we get, 5 root 3 I cap plus 25 k cap radian per second. Therefore, the magnitude of angular velocity of the spool is the magnitude of this vector, which turns out to be 26.5 radian per second. Next, we have to find out the angular acceleration of the spool. If I derivate the angular velocity of the spool, then I get angular acceleration, and when I do the derivative, I must remember to take the derivative in our prescribed form. We have the local derivative, plus because of the frame rotation we have another term omega f cross omega spool. Now, because these magnitudes are constant, therefore, the local observer who is fixed to the x y z frame will not see any local change. Therefore, del del t term goes to 0, and what remains is only the omega f cross omega spool, which is because of the rotation of the frame. And if you plug in these expressions, we have omega f cross omega 1 plus omega a, but remember omega 1 is same as omega f. Therefore, this cross product will vanish, the first term will vanish, and we have omega f cross omega a, and that will be the angular acceleration of the spool. And if you do this calculation, then it is minus 100 root 3 j cap radian per second square. This completes this problem. We are going to move to the next one. If the motor shown pivots about the x axis at a constant rate d gamma dt equal to 3 pi radian per second with n equal to 0, determine the angular acceleration alpha of the disc as shown of the disc as the position gamma is equal to 30 degree is passed. In the figure you can see this is the angle gamma and this is n, n is given to be 0, it is fixed. The motor is spinning and this gamma is increasing at 3 pi radian per second. The constant speed of the motor is 120 revolutions per minute. Therefore, we are specified this omega naught, which is the spin speed of the disc. Also find the velocity and acceleration of point A is shown in the figure. which is on the top of the disk for this position. At the instant point A is a point on the circumference of the disk. At the instant A reaches the topmost point, at that instant you have to find out the velocity and acceleration of point A. Some dimensions are specified. Take OC as 25 centimeter and CA as 12.5 centimeter. These dimensions are specified. We will use this XYZ coordinate frame. Z is the spin axis, x is the the small x is also the capital X axis in the opposite sense, about which the gamma is changing, and y completes the right handed coordinate system. In this XYZ frame, I am going to express all vectors. Omega naught is the spin speed, therefore, omega naught vector is the spin angular velocity, which is 4 pi k cap radian per second. Frame angular velocity, the frame is rotating because gamma is changing. It could have rotated also if n were non-zero, but since in this problem n is equals to 0, therefore, the frame is not rotating because of n, it is only changing because of gamma, and that is expressed as minus 3 pi I cap. You must note that gamma is increasing at 3 pi radian per second in the counterclockwise direction as seen from the capital X axis. Therefore, with respect to the small x axis in which we are representing everything, it is minus 3 pi I cap radian per second. Therefore, angular velocity of the disk, net angular velocity of the disk is angular velocity of frame plus angular velocity of the disk with respect to the frame, omega f plus omega naught, and if you do that, this is the result, minus 3 pi I cap plus 4 pi k cap radian per second. Angular acceleration of the disk, I must take time derivative of the angular velocity, and following our prescription it must be local change del del t of omega plus omega f cross omega. And since these things are constant, omega naught is the magnitude of this is constant, magnitude of omega f is constant, therefore, there is no local derivative. Here you should note what is meant by this local derivative. Had these values, had these been a function of time, then you would have local derivative. The other part comes from the frame derivative, this I cap vector dot k cap vector dot, that sits in this term. Since the magnitudes of omega naught and omega f are fixed, they are not time dependent, therefore, the local derivative vanishes, and what we have is the angular acceleration because of the frame rotation, omega f cross omega naught. Why only omega naught? Because in omega you have this in omega you have both omega f and omega naught, and omega f cross that term, omega f cross omega f will be 0, and therefore, we are left with omega f cross omega naught. And if you do that calculation, it turns out to be 12 pi square j cap radian per second square, that is the angular acceleration of the disk. Now, we have found angular velocity of the disk, net angular velocity of the disk, angular acceleration of the disk, and we now transform to the capital X Y Z frame. How to transform? We must represent all these small I cap, j cap, k cap in terms of capital I cap, j cap, k cap. For example, here I have I cap, here I have k cap, here I have j cap. If I can express these unit vectors in terms of the unit vectors along capital X, which is capital I cap, along capital Y, which is capital J cap, and capital K cap, I can easily express them. If you look at the figure, then I cap is equal to minus capital I cap. As you might have noticed that capital X and small x are in opposition, therefore, I cap must be equal to minus capital I cap. J cap is in this direction, y direction. If I express that in terms of capital X, Y, Z, Z is of course the vertical, this is capital Z. I can express j cap in terms of j cap, capital J cap and capital K cap. Capital J cap is along capital Y and capital K cap is along capital Z. Therefore, that representation becomes minus sine gamma j cap, because it makes an obtuse angle with capital Y, therefore, minus sine gamma j cap plus cosine gamma capital K cap. Similarly, K cap, which is along the spin axis, can be represented in terms of capital J cap and capital K cap. Once you use those transformations, you can represent all those vectors in capital X, Y, Z frame. Now, let us talk about the velocity of point A, which is the second part of the problem. We have to find out velocity of point A and acceleration of point A. Velocity of point A I can express in terms of a convenient point, which is O. Velocity of point A is velocity of O plus V rel plus omega frame cross O A. Now, I just write down these vectors in terms of what is given. V rel is because of the spin of the disk, therefore, it is omega naught vector cross O A plus omega f cross O A. Now, these expressions are all known to me. O A vector, because the dimensions are given, this O A vector is O C vector plus C A vector. These dimensions are given, therefore, we have the expression of O A vector, and if you plug in all these values, velocity of point A turns out to be this expression, meter per second. Now, acceleration of A, this is our master equation. We discussed this in kinematics. Acceleration of A is acceleration of point O plus A rel because of the spin of the disk plus alpha frame cross O A plus omega frame cross omega frame cross O A plus 2 omega f cross V rel, and V rel we know is omega naught cross O A. This is V rel. Therefore, we have expressions for all terms. If you just plug in, and the only thing is angular velocity of the frame. If you find out angular velocity of the frame, you will get omega f is equal to del t of omega f, which is the local derivative, plus omega f plus omega cross omega f is always 0. Therefore, this is 0. Acceleration, angular acceleration of the frame is 0 in this case, and A rel we have discussed this. We already know V rel, we want to know A rel. A rel will have centripetal term. There is no tangential term because omega naught vector has a constant magnitude. Therefore, only the centripetal term exists for A rel, and that turns out to be like this. If you plug in all these expressions in the acceleration of point A, finally, we have this as the acceleration of point A in meters per second square. These things you can check. To summarize, we have started with discussing the kinematics in 3 dimensions. We have looked at a prototype problem of an axisymmetric body rotating about a fixed point, and we have looked at some examples. With that, I will close this lecture.